Hello everyone. In the previous video, we solved the two-sum problem using brute force approach and the dictionary approach. The brute force approach uses constant extra space, but its time complexity is O of n square. The dictionary approach improves the average time complexity to O of n, but it requires O of n additional space. In this video, we will look at the two-pointer approach, which will give us time complexity O of n and space complexity O of 1. However, there is one important condition. The input array must be already sorted. Let us use this sorted array 1, 2, 4, 6 and 10. And suppose our target is 8. We place one pointer at the beginning of the array. We call it the left pointer. We place another pointer at the end of the array. We call it the right pointer. Now we calculate the sum of the values at these two positions. Initially, it will be 1 plus 10 equal to 11. Our target is 8, but the current sum is 11. The sum is too large. So we need a smaller value. Because the array is sorted, moving the right pointer one position toward the left gives us smaller number. The right pointer moves from 10 to 6. Now we calculate 1 plus 6, we will get 7. This time the sum is smaller than our target. Because the array is sorted, moving the left pointer to the right gives us larger number. The left pointer moves from 1 to 2. Now 2 plus 6 equals 8. The sum equals the target. So we have found our answer. The matching values are 2 and 6 and their indices in this sorted array 1 and 3. Why sorting matters? The two-pointer approach works because the values are ordered. When the sum is too small, we know that moving the left pointer rightward will increase the sum. When the sum is too large, we know that moving the right pointer leftward will decrease the sum. Without sorting, moving a pointer would not reliably tell us whether the next value will be larger or smaller. That means the two-pointer decision would not be safe on an unsorted array. For an already sorted array, this approach provides time complexity O of n and space complexity O of 1. It uses only the two pointer variables and a few temporary values. Now let us look at the swift implementation. Our function receives a sorted integer array and a target value. It returns an optional array because there may be not a valid pair. First, we check whether the array contains at least two elements. We need at least two different elements to form a pair. Next, we place the left pointer at the first index and we place the right pointer at the last index. We continue while the left pointer remains before the right pointer. Using left is less than right ensures that the two pointer never refer to the same element. Inside the loop, we calculate the current sum. Then we compare this sum with the target. When the sum equals the target, When the sum matches the target, we immediately return the two indices. When the sum is smaller than the target. A smaller sum means we need a larger value because the array is sorted in ascending order. We move the left pointer one position to the right. When the sum is larger than the target. A larger sum means we need a smaller value. Therefore, we move the right pointer one position to the left. It means we have to minus our right pointer. If the pointers meet without finding a matching pair, the loop ends and the function returns nil. For this example, if we call this two sum sorted function with our array and with our target, then we will get output 1 and 3. The value at index 1 is 2 and the value at index 3 is 6. So we will get our target 8. So if we see at this function, then we'll get to know the time complexities of n. Although we have two pointers, they do not restart or move backward. The left pointer only moves towards the right and the right pointer only moves towards the left. Across the complete execution, each pointer can move at most n position. Therefore, the total work remains linear. The space complexity is of 1. We use only a fixed number of variables, left, right, sum. The amount of additional memory does not increase with the size of the array. When should we choose this approach? Choose the two-pointer solution when the input array is already sorted. Returning position from the sorted input is acceptable. You want O of n time. Constant extra space is important. Now let us go through the execution step by step. Our input is 1, 2, 4, 6 and 10 and our target is 8. So our first iteration will be like this. Our left pointer will point to index 0 and our right pointer will point to the index 4. So the values are 1 and 10 and their sum is 11. Since 11 is larger than the target 8, the sum is too high. Therefore, we decrease the right pointer. Right equal to right minus 1. And the right pointer moves from index 4 to index 3. So our second iteration will be left pointer will be at 0 position and right pointer will be at third position. And the values are 1 and 6. So their sum is 7. Since 7 is smaller than 8. The sum is too low. Therefore, we increase the left pointer. So left is equal to left plus 1. The left pointer moves from index 0 to index 1. So our third iteration will be left 1, right 3 and the values are 2 and 6. So we will get our sum is 8 and that is matching with our target. Therefore, the function returns 1 and 3. Notice that with every pointer movement, we eliminate several impossible pairs. We do not need to compare every element with every other element as we did in the brute force solution. Important limitation. So, the two-pointer approach does not work directly on an unsorted array. For example, consider if we have an array 6, 1, 10, 2, 4. Moving the left or right pointer does not reliably increase or decrease the sum because the values are not ordered. We could sort the array first, but that creates two additional considerations. First, sorting changes the time complexity. Sorting normally requires O of n log n time complexity. Second, sorting changes the original positions of the values as well. If the problem requires indices from the original unsorted array, we must preserve each number with its original index before sorting. For example, we could create tuple containing. Then we sort those tuple by value and return the stored original indices after finding a pair. That approach works, but it is more complex and may require additional memory. For the standard unsorted two-sum problem where the original indices are required, the dictionary solution is usually more direct solution. The two-pointer approach is especially useful for a large already sorted array where the constant extra space matters. So now let us quickly compare the three approaches we have covered. Brute force having a time complexity O of n square, space complexity O of 1. Dictionary average time complexity is O of n and space complexity O of n. Two pointers unsorted input time complexity O of n, space complexity O of 1. The two-pointer approach provides an excellent combination of linear time and constant extra space, but it depends on the array being sorted. So we should not select an algorithm based only on its big O complexity. We must also consider whether the input is sorted, whether the original indices are required, whether the additional memory is acceptable, whether modifying or sorting the input is allowed. Thank you for watching. In the next video, we will compare the two-sum approaches and understand when each solution is the most appropriate choice.